Hello everyone, my name is Leonhard Faube and I wrote the paper Is MLOps Different in Industry 4.0? General and Specific Challenges together with Klaus Schmidt and Holger Eichelberger, which I will present to you now. The paper is about how MLOps works in Industry 4.0 and what challenges this poses. And first I'm going to present what MLOps are and why to use it. And then I'm going to introduce MLOps in Industry 4.0. And finally, I present our identified challenges and conclude the paper. So let's start with an MLOps definition. MLOps are tools, practices, and processes for machine learning deployment in production. They help to automate, for example, in terms of pipeline automation or workflow automation and automation of machine learning tasks. Further, they include monitoring and sometimes triggers to retrain the model as well. And versioning is also part of MLOps to store the current versions of data and models and code and configuration whenever a change is made. Let's now try a more practical approach to machine learning operations. What would happen without MLOps? Without MLOps, some difficulties would arise when using machine learning models. For example, real data behaves differently than a constant training set. Since data in the real world can change constantly over time, models stop working after some time. And in that case, the model needs to be retrained or even adjusted in some way. It must be manually detected when a change has occurred and a correction must be initiated. For phenomena like changing data, no trigger is available to initialize the retraining automatically or to initialize the training at all. When repeating the individual machine learning steps, there are potential errors that occur when performed manually. That slows down the process and potentially leads to high costs. It's also unclear when experimenting which models were trained with which data feature and which configuration to get a particular result. Furthermore, we don't think about the quality in beforehand of the models, for the quality is only captured when they are used in the real world. Since machine learning is increasingly used in Industry 4.0, it is important to consider what happens in that specific case. Now we know about MLOps, about what they are and why we should use them. But how does MLOps work in Industry 4.0 then? At first, we start with an initial problem or business idea that we want to solve. With a manual step, we investigate if and how the problem can be solved and which algorithms work best to solve the problem. Then we have to think about the high-level architecture. So which infrastructure have we got in the productive environment? Which requirements have we got then? We have to adapt the machine learning model to these requirements. Further, we automate a pipeline, for example, to solve our problem and deploy it to the production environment. By applying the model, we look for data drift, so changing data for model precision and other things to monitor the quality and to determine if the model is still working properly. If it's not, we try to reinitialize a training on the existing hardware architecture. If we are not successful in that, we might even need to go back to the business problem and rethink the model from scratch, including the high-level architecture. We have three things we try to automate. In that context, we can use kind of the ICD workflow for the model to continuously deploy and test. Further, we can also automate the workflow of the pipeline for the training and also the machine learning steps like data preparation or model training, can be partly automated to figure out the best procedures and model hyperparameters. This was a rather abstract explanation of MLOps in Industry 4.0, but now let's think about the details. We have taken a look at the literature to find out the most common activities related to MLOps and put them in an MLOps lifecycle. So other MLOps lifecycles focus on the relation to DevOps principles, but here we focus on the activities, including the data engineering, model engineering, operations, and support activities. They all depend on the overarching high-level architecture in an industrial environment. Considering these activities, we were looking to challenges in the context of Industry 4.0. Now let's take a look at these challenges we faced. Challenges exist in all four task groups of our MLOps lifecycle: data engineering, model engineering, operations, and support activities. We first start with data engineering related challenges. In the data collection, there are cases where technical prerequisites in the factory floor environment are not met. We need specific information in accurate time intervals delivered by sensors and transmitted to the machine learning component. If suitable sensors and data transmission are missing, we have problems to meet the requirements for our analysis in some cases, and additionally, we need real-time and big data processing sometimes. And for that reason, we need to convert or adapt to existing hardware and software, which causes a big effort if it's possible at all. In the data preparation process, we need hardware on the factory floor, which is fast enough to pre-process the data as well. Specifically, we require sometimes high-performance hardware and software to process the data in real time. And however, in many cases, not every solution is applicable due to the availability of hardware, which is limited by factory floor regulations and also by budget. These factory floor regulations include rules like data protection laws, internal company regulations, or even relays for companies that require protection. And sometimes customers don't want to change in their existing hardware infrastructure because the production line must not be interrupted, and possibly the complexity of maintenance and repair should not increase additionally as well. And in some cases, it's even restricted to provide an external network connection or a data connection. Now let's take a look at model engineering related challenges. For model building, training, evaluation, and selection, we want automated training within the factory environment. For this, we need additional hardware resources and software infrastructures. For example, for embedded devices. In the model packaging, we package a model, code, and configuration together with all dependencies that are necessary. Here, the constraints of the available hardware resources must be taken into account, which was often a problem. The hardware resources can be special hardware like GPU, TPU, or FPGA, and also the network bandwidth, operating systems, and storage capacities are sometimes limited, adapted, or unique for the use case in the production environment. Next, I will show you the operations-related challenges. CI means continuous integration, and CD means continuous deployment. And for CI/CD testing, we want to perform tests within the integration and deployment process, we need to consider the heterogeneity of hardware and software described above. It's often more complex than usual, which leads to additional tests on the machine learning infrastructure and monitoring tests and so forth. We also plan to investigate the automated adaptation scenario, where tests happen within the factory environment. In the monitoring, we sometimes face the physical separation of groups and networks. And here we have additional hardware and development efforts to provide a connection in some way. So now let's go further with the infrastructure challenges. One of the biggest challenges is the heterogeneity. There are embedded devices, so devices that contain a special purpose computing system. There's also corporate IT, so there are restrictions on IT that cannot be bypassed. And when we got automated model engineering activities, they're sometimes not fast enough on a server and even need to run on embedded devices, for example. Also, the implementation of existing computing frameworks on the factory environment is sometimes tricky, since they have sometimes to be adapted to the specific use in the particular situation. Further, missing standards are difficult to handle, since there are legacy machines that do not support the communication with another system, so they are not smart. There are retrofitted machines, which are machines that are refurbished or updated to support external communication and smart capabilities. And there are also standardized machines. However, they have many different standards and not one standard. So very different machines with many different standards can be found here. Now let's conclude. MLOps are the key to successfully implement modern machine learning-based software solutions. And we have identified several MLOps challenges in Industry 4.0. Most of these challenges exist in similar manner in more traditional software engineering contexts, but we found 4 challenges that particularly occur in Industry 4.0. So most challenges are not unique to Industry 4.0, which is a positive indicator for using existing technologies and practices in this context as well, and adapt them to the specific needs in Industry 4.0. We will further study these challenges in more detail and address them in the future. For that reason, we plan to conduct industry studies and apply our knowledge to frameworks. Thank you very much for your attention. I would be happy to answer any question you may have now.